Thank you again for the introduction and this really exciting opportunity to present here at FAR.AI Lab. And today I want to share the vision of founding new academic disciplines like physics, psychology, and neuroscience of AI to achieve this ultimate goal of AI safety. And I think that goal is now already shared, but I want to present my version of it to give motivation. And I think as everyone here is almost like feeling every day, I think yesterday we had the Anthropic announcement of the computer use of with AI engines, etc. I've been in this field more than 5-7 years now, and I think by witnessing this pace of progress, I think there is almost no doubt that the AI is already capable and will become capable. And if we think in the almost like academic timescale, which is like a decades or even century, the question of whether AI will be capable at the end of this century is no longer almost a question. We're going to have it. We almost have it, right? And then the remaining question that is a really open question right now is, can we make it safe or not? And I have my version of it. So I come from Japan. And then one thing that I feel in talking to my Western friends and let's say my local friends in Japan is that I think a lot of our mental picture of what AI is, it's really painted by the movie that we see growing up, right? And in Western world, like iRobots, Terminator, I think I'm just only naming a few of them. But then there is this a picture that, okay, super intelligent AI models, which is like embedded as a humanoids. They're fine in the beginning, but then they turn like a villain and then destroy the world, right? But then I don't know why, but as I grew up, like a lot of the super intelligence that appears in Japanese anime and stuff are all like human friendly. I mean, I'm just showing two of them, but there are just many more of them, right? And Doraemon is almost like, almost shaping how Japanese kids think about ASI growing up. And then maybe even some people didn't know about Doraemon, or maybe they didn't know that it's actually meant to be a robot. It came from 21st century or something. It's a robot. And then the only thing that Doraemon does is to resolve conflict among humans and help them with tools, right? And again, my goal as an academic researcher is to really just fill the gap of, okay, in the industry side, there's a lot of progress happening in terms of increasing AI's capability. And then, of course, there are a lot of practical works being done to almost like tape all the models that will be shipped right now to make them safe. But then I think if we look at the longer term, there really needs to be foundational science about it, defining what it means to be ethical, defining what it means to be trustworthy. And then the academia, I think, has still a lot to offer in terms of not just mathematical computer science, but also in terms of social science. And the vision that I have is to integrate all the resources that academia has towards building some foundational scientific fields for AI safety. And I want to start my own, discipline that I grew up, which is physics, right? And then I think one biased way to summarize all the industrial revolution that has happened so far is this repeated history of understanding and controlling complex systems for engineering and industrial use cases, right? And I think I've been kind of pitching this physics of AI for over 5-6 years now, but then I think I don't need to justify so much anymore because the Nobel Prize just in physics just went for AI. And then if anything, this John Hopfield, I think everyone knows about Hinton at least, but then John Hopfield is a physicist, who is my academic ancestor, and then I had a lot of indirect or direct influence in terms of how I think about physics of AI. And just to give you some of the example, here's a steam engine and thermodynamics. I think this story often pops up. Like it almost took 50 years for the steam engine to get this ChatGPT moment, and another half century until these physicists came in to formulate the principle of thermodynamics, which, if anything, underlies a revolution of like diffusion models, right, etc. And then the repeated trend is, okay, next is a semiconductor or the computer hardware stuff, and then it's driven by electrons and many-body electrons. We need a new kind of quantum mechanics, like many-body quantum mechanics for it. And then the display that I'm looking right now are liquid crystal displays, right? So it's really controlling all the polymers and everything with a high precision by applying external electric magnetic fields. And then there's this soft matter physics, which has developed together with chemical engineering that I'm going to come back in the next slide. And then the point is, okay, if we extrapolate this trend of every time complex systems previously in nature, turn out to be useful, we need to understand and control them. And I just see science of AI as just a continuation of this trend. And the statement again here is that AI is AI is frontier for everything right now, but then AI is also for the new frontier for physics. And to further motivate the analogy in terms of safety, I want to come to this particular example. As I said, chemical engineering has been one of the major progress field in the last century, where a lot of chemical factories are built to rapidly synthesize chemical materials, as a basis for our, let's say, our clothes that we are wearing, or the nylon, etc. And then this chemical plant, which is a Philipsboro disaster. So there was this big incident that happened toward the end of last century, or where the cause was really the intense capitalistic pressure. Like so many companies are building factories, and then a lot of competition for synthesizing materials as cheaply as possible, as quickly as possible, shipping them. And what happened was that in the factory, so there are like 6 chained reactors, right, like this. And then this reactor number 5, someone found some crack. But then, okay, so it's a safety issue. Okay, there is a crack in the reactor 5. And then if anything, these reactors are really under high pressure because they are synthesizing some chemical materials. But then what's going to happen when people are under extensive pressure is to say, okay, let's just put some little pipe to bypass this thing, skipping this reactor 5 so that the factory can just keep operating, right? And the consequence is, in the hindsight, kind of obvious. So they put this 20-inch bypass to these reactors, and then the pipe failed due to unforeseen pressure, resulting in catastrophe, right? And then there were roughly 72 workers who are working on site, but this was because it was a weekend. But still, the number of people who were there are smaller than the weekdays. But close to half people, 28 people, were killed, and the 36 were seriously injured. And then what happened right after, so almost within that year, this UK Health and Safety at Work Act went through, and then this is like one of the major safety policy that came in toward the end of last century, right? And then I think all of these lessons from like a scientific governance and then all the industrial capitalistic pressure is something that we can think about as like one of the analogy when we think about AI safety, right? And then I want to reinforce that, I think it's really worth emphasizing scientific foundations are critical, just like how we need thermodynamics, chemical physics to think about, okay, if we increase this pressure a little bit, what's going to happen to the pipe? The similar question is there in terms of thinking emergent abilities in AI models. And also, I think this danger of capitalistic pressure is worth noting. Again, everyone wants to ship safe product, but then also everyone who's participating in this capitalistic competition needs to ship it fast because you're going to be lost in the market, right? And then there really needs to be some regulation, which is informed by science, just like in this case, everything has happened after this incident, but this time we want to do it before. And with all of these motivation, we started this program called Physics of Intelligence program at Harvard this April. And I'm really proud that this is at least partly creating some really nice academic setup for students and postdocs to think about these issues together with really deep foundation of science. And then I myself as a physicist, but then I belong to Center for Brain Science. And the building that I'm sitting in is a social science department at Harvard, in particular psychology department. So leveraging all the industry funding and everything, we are building really interdisciplinary team to think about these problems. Right. And this is today's agenda. I want to talk about 3 topics. The first 2 is about emergence. So the first one is the multimodal synthetic data to better understand compositional generalization of diffusion models. And I'm going to present really high-level takeaway that the more compositional an ability, the more suddenly it emerges. And I believe that this top punchline is really relevant now because all the agents use a lot of tools, and then they compose them to achieve the long-term goal. And what I would predict based on the scientific observation here is that the agentic capability can really emerge like even more suddenly than the previous more atomic capabilities. For the second one, I want to go deep into this emergence of abilities in LLMs. In particular, we create a synthetic dataset using probabilistic context-free grammar, synthetic grammar, or the synthetic pipeline to generate language from linguistics. train transformers, and then test our theory of percolation phase transition theory of emergence. Finally, I think there was another headline this morning saying there were some teens who went through suicide, which is like really disastrous thing due to potential emotion manipulation by AI bots. And then I have been thinking about the problem for the last half year, which is to better understand how AI represent emotion. And then there is a paper that we just submitted with a Harvard psychologist in collaboration about how AI might be representing emotion, what kind of bias can be there, and how that might interact with a persuasion. So this is a agenda for today. Let me first introduce all the amazing collaborators. So all of our projects are really collaborative, and I really want to give credits to everyone who deserve. So first of all, Ekdeep is amazing, previously a student at Michigan, but then now joined as a postdoc with us. He's been thinking a lot about AI safety, in particular in collaboration with David Kruger. And then he's the one who set up this amazing synthetic multimodal data setup. And Maya led the execution of the first work of the compositional abilities emerging multiplicatively last year in EURIPS that I'm going to talk about first. And Corey has been responsible for the follow-up work that we again will present at EURIPS. And Yoni has been amazing theorist who took all the empirical insights and turned into theory. And Andrew has been helping everywhere in terms of like empirical execution. And Robert and Wei Hu are amazing. They're some of their advisors who I have been collaborating, fortunately. Okay. So the question that I want to start with is, what do we mean by novel or creative, right? And there are two contrasting examples. The first one is this coming from this paper, understanding and mitigating copying in diffusion models. So when AI models generate something, there's a natural question of, is it just taken from the data set, retouching it, or something truly novel, right? The bottom lines are the original data. Top rows are AI generated. As you can see, these are quite similar. But then when we have first seen DAO-E, like everyone was, okay, avocado chair, like astronaut riding on a horse, there were some sense of like a novelty here, right? So the question is, how do we even like mathematically try to capture the difference between the two? And as a physicist, like our approach is to really ask this question of, as Einstein said, what is a kind of setup system that is as simple as possible, but not simpler? Not simpler in the sense that it's not going to miss any of the key feature of the phenomena that we are trying to study. And one consistent approach that we take is the design of the synthetic data, because among the 4 ingredients of deep learning, loss, task, data, and architecture optimizer, one thing that people least control upon when we do scientific studies is data. But then I increasingly believe that the data can be one of the, if not the most important ingredients among the ingredients consisting deep learning models. And in this particular case, the simple task that we have created is this. So you have tuple, which is kind of replacing the text and image. And then if you see 3 combinations of tuples and image, the question is, what is 2B? Any guess? Yes, intelligence. It's okay. So that exactly the intelligence is my point, right? It's like blue triangle. Okay, and then there's a shape and color. I think the kind of little brain exercise that people probably have done is to try to associate, what 1 or A means in terms of the visual feature that you can see in the image. And this is exactly the kind of process that diffusion models go through when it tries to learn to generate novel data, right? And we can put some simple mathematical framework on it. So maybe someone in the computer science knows this as a Hamming graph, but then the way we view the system is, okay, like each axis here is a shape axis, size axis, and color axis. And then we can almost define some semantic distance between set of objects, pair of objects, by just counting how many of the attributes or concept variables that we call are different from given a pair of objects, right? And what this kind of framework allows us to do is a theoretical characterization, but also empirical characterization, in the sense that people have been asking this question of, can diffusion model generate something truly outside of distribution? This definition of compositional generalization was almost impossible without synthetic data setup. So what we have done is to create this synthetic data, which has all the geometric objects except for the one with the question marks. And in the training data set, we never put any object which is a question mark, and only put all the solid objects, right? And then this is abstraction of the one level, more complex one is that we also studied in parallel is this a survey data set, but then we have categorized each of the image based on the attributes. And we did something similar in terms of not showing everything, only showing part of the data set, right? And then now we can ask whether the model can truly generate something that the model has never ever seen in the training set, because we are the one who control the data. And these kind of concept graphs that we call are also partly motivated by the clip embedding. So if you one way you can think about it is that we are just assuming that the clip embeddings are kind of already disentangled, and then if you do PCA in clip by putting these objects, well, you can actually extract the cube out. So in this setup, we're kind of assuming that the clip has already disentangled concepts, and then thinking a lot about how diffusion model gonna do it. So the two questions that we're gonna ask is, can a diffusion model generalize to concept classes that it has never seen before in a training set? And we are also interested in the learning dynamics, right? If so, what is the order in which the diffusion model learns to generalize? And this is a video where it's showing the inferenced output from the diffusion model as we train the model. So in the beginning, all the images were random because the parameters were initialized randomly. But then as the training makes progress, you can start to see more cleaner and cleaner images of the expected outputs, right? Well, try to check. Right? Okay. And then what you can see is that I think around this point you can now see that the diffusion model can actually disentangle these shape size color axis and then generalize. And then even before this work, even this was not trivial at all for people. And then this is one of the first demonstrations that text condition diffusion model can compositionally generalize in concept space. And to make things more quantitative, what we have done next is to plot the accuracy of the generated objects as a function of the optimization time. And what you can see is that all the objects which is distance 1 away from the training set. So the blue curves are the in-distribution samples, and the pink samples are 1 step away from the training set. And then this one is almost like diagonal from any of the training set sample, which shows this really emergence-like curve, which is hinting at something. Right? And then I am going to just point out some visual similarity between, I think now really famous Jinsou Wei et al.'s emergence curve, and then our learning curve for 2 distance away compositional generalization dynamics curve. Right? And then the question is why? Again, it was like last year, and then I think this synthetic setup can really offer intuitive explanation of why this is a case. And okay. Yep.
What are so I don't really understand why these bases are the natural bases that you consider, and I see from the figure that 2 is further away from the node, but from a data set point of view, what property did you instill such that 2 is further away? Does that make sense?
Okay, I think
I can reconstruct the data set in the sense that 2 is closer to the original. I can imagine a world like that. So what about the design such that 2 is further away?
Okay, so I think there is nothing in the data generation process that is explicitly saying 2 is farther away. So I almost consider this cube as a model as opposed to the whatever ground truth of how distance should be measured. To make it more concrete, another distance measure that I could think about is just, let's say, some pixel-wise distance, right? You have 2 images, and then represent 2 images as a vector in this pixel space, and then measure the, let's say, L2 distance between the images, right? And then the point here is that we hypothesize that this semantic distance captures this generalization dynamics better than any other distance measure that we can cook up. So this was a hypothesis, and this is a confirmation that this concept distance that we define is a better proxy for predicting the learning dynamics. Yeah, thank you. And I think another thing that I want to point out is that some people may argue that, okay, you see these rather sharp learning curve because that's the way we created the training set, created the data. But then maybe before going to the next slide, one thing I want to point out is that the in-distribution sample has really smooth learning curve. And then the question is why only the out-of-distribution sample show these rather nonlinear, non-monotonic learning curve. And then our explanation is really simple. So if the model needs to learn multiple capability, in this case, the capability is to transform shape, transform size, and transform color. So these are the 3 atomic capabilities that the model needs to learn to out of distribution generalize. If that's the case, learning curve for each of these shape accuracy, size accuracy, color accuracy, independent evaluated should be multiplied to get to this multiplicative loss function, right? And one of the takeaway here is that the composition is really an and condition, not an or condition. And additive metric would imply that if it's or, which is this additive case, the learning curve should be really smooth. But then if the task is truly multiplicative, it's gonna be more likely that the learning curve is sharper and sharper. And one thing that I want to mention here is that the one hypothesis that we are testing based on this insight right now is that the agentic capabilities are typically more and more compositional, in the sense that if the model needs to use computer and then use a set of, not just one, but multiple applications to complete some task, or if someone wants to use set of mathematical knowledge and then compose them to write down some really massive proof or something. So if the capability that we are going to evaluating is more and more compositional, then there's a higher chance that the emergence curve become even sharper and sharper. Right? And then this is a really toy model. I can, it's in the paper, I can explain more, but in this toy model, n is a number of capability that the model is composing. And as you can see, if you increase the number of capabilities that you can compose from like 1 to 20, the things get sharper and sharper. So it's a really, I think, translatable insight there. And as I put physics, I think about practical problems, but I also care about doing science to the end in terms of from empirics to the real theory. And then we made further progress in terms of representing learning dynamics in concept space. And I think this concept space idea is, I think, really intuitive if you think about this particular example where through the course of scaling, the model was asked to generate blue square apples. This is from another paper. And then what you can see is that the smaller models can only show yellow round apple, but then as the model becomes bigger and bigger, it next generates round blue apple and round square apple, right? And then we have pitched the idea that we should project all the learning dynamics in concept space where each of the axes are independently measuring the accuracy for color generation and size generation. And each of the trajectory that you can see is, all the model at initializations are all the dots here. And then as the model gets trained, it's gonna, depending on the way that we construct the data set, in particular, this blue curves corresponds to data set where the contrast between the color is really small. Because of that, there is not much color signal coming in because the color contrast is small, right? If that's the case, the model gonna learn size first and then color. If the contrast for the color gets big, it's gonna learn color and then size. So this is like one really simple answer to the question of, okay, what determines whether one concept gets learned first or second, right? And then this was the in distribution generalization learning curve, but for out of distribution, we're gonna see much more richer curve, including there is a trend where it goes to the left, going farther away from the ultimate generalization points. And then, for example, sometimes it's not gonna even come back. And then, there are some richness that I'm gonna explain in the next slide. And another kind of question that we can ask in this toy simple synthetic scenario is this notion of hidden capability. People talk about hobbling, etc. But then even this really, the point is that even this tiny simple synthetic data set has something like that. And what we have shown is that if you benchmark in terms of out of distribution generalization accuracy, in this case, generating blue circle was the out of distribution sample that the model needed to generate. But then if you naively look at the learning dynamics and see what are being generated, it's just red circle. So the model naively couldn't perform the task. But then what we have found is that if we do either over prompting, saying instead of saying, oh, please generate blue circle, let you say like a blue by increasing the RGB value that you input to the text domain, or if you do some surgery in its representation, the model can the model that seemingly couldn't generate these blue circle suddenly were unlocking the capability to generate this auto distribution sample. And we have consistently seen this both in the survey as well as even the stable diffusion. So what you can see is without latent linear intervention, what you get is these female without a hat. So the data set now is okay. So male with a hat, male without a hat, female without a hat, and then we never show female with hat in the training set. But then, as you can see, if you train the model, but then also apply some latent linear intervention techniques that we propose, you can generate it. And we can see the same thing with stable diffusion, where the prompt is to generate triangle credit card. And without it, it couldn't. But then this surgically in this representation can unlock this capability. And then finally, I don't want to go too much into the theoretical part because it gets technical, but then I want to share some of the high level idea, right? So the idea is you have some real complex phenomena with real data sets, and then progressively simplify the data so that in a way that you still don't lose this essential phenomena of compositional generalization. And then we could go to some like analytical theory by further simplifying these axes with Gaussian, multivariate Gaussian distribution, which is centered at part of the nose of this cube, right? But then if you go to the single full Gaussian blob, we're going to lose all the phenomena that we've seen in terms of compositional generalization. So this is where we stop at in terms of complexity reduction. And then we have a theory. And then the task that we propose is actually like an identity learning task. So the task is to get inputs of these multimodal Gaussian random variables and then output the same variable. But when the network initializes at initialization, it's going to just map this input to randomly anywhere. If you train the model, it's going to quickly learn to generate for in-distribution samples, but for out-of-distribution, you have to train. So that's the kind of setup. And you can do some calculation and analytically solve it. And high-level takeaway is that in experiment, we have shown a set of phenomenology. The first one is how Hamming distance or concept distance on the graph dictates the learning dynamics, the way the model generalizes out of distribution. So that phenomena is captured. Next, we had this phenomena in terms of learning dynamics in concept space, and then that can also be captured by this analytic theory. And finally, I think the real benchmark for theory is, is it going to make any prediction about what we should see in experiment? And then we have that too. So what we have analytically shown is that the out of distribution learning dynamics can be really highly non-monotonic, right? So if you're training models, the in-distribution train loss should always go down if you're, let's say, using gradient flow, right? Because gradient should keep guide the model to lower and lower loss. It might get stuck at some local minima, but it should never go up. In contrast, if you think about out of distribution loss, there is no constraint like that. It's free to do whatever you want, and then that's what we see in our theory. And there are some explanation about how different modes coming up in the weight learning dynamics can shape this non-monotonic curve. But we have then tested what we have seen in this theory with real diffusion models. What you're seeing is now y-axis is an error. So what you're seeing is that there is some learning happening, but then in the middle, the error goes up and then go down again, right? And intuitively, I think I shouldn't make too much of an analogy because it's a learning dynamics versus scaling, etc. But then even in language models, there are reports of U-shaped learning curve, where I think the intuition here is that as a model tries to learn each of the different concepts, there is something like transient memorization, right? So I think one of the example here is that what you're seeing is at initialization model just generates something close to the origin. It's going to be attracted to each of these points sequentially, but when it's get attracted, there's this like a curving learning dynamics, which is going to be leading to these transient going up, right? So memorizing some of the training solution can negatively contribute in terms of the progress of the out of distribution samples, and then that we capture with this analytic model. Yeah, so in terms of the takeaway for the first part, I think I've shown is that like the one is the approach of using synthetic data to carefully study this phenomena of auto distribution generalization and compositional generalization. We have seen how multiplicative effects coming from learning each of the atomic capability and composing them can lead to really rapid learning curve. In particular, I think we will see that in agentic models. And then we went to some theorizing and then found that these transient memorization can lead to U-shaped learning curve. So next, I'm going to move to the percolation theory, trying to explain this emergence phenomena in language model with a formal notion of phase transition. And this work again was led by Ekdeep, now the postdoc with a group that I've just explained in the previous work as well. And Kyogo, who is a theoretical physicist at the University of Tokyo, my long-term friend, and Ekdeep's advisor for his PhD, Robert, at University of Michigan. And it's on archive, so you could see it. So coming from physics, it's been really great to hear the word emergence everywhere. But then at some point, I was also slightly frustrated because people are even arguing whether something is emergence or not without definition. It's just, what is emergence? And then I don't think anyone has any formal definition here because, first of all, the phase transition in physics is equilibrium system sitting almost like still in a slowly changing parameter versus people are, scaling up the system or, looking at the learning dynamics, which is like fundamentally out of the equilibrium. So this is something that we should almost each time define ourselves and then only then discuss whether something is emergence or not. That's my first rant. But for this work, what we have started by saying is that this notion, this notion of order parameter in physics is really important, I think, in terms of thinking about emergence, right? So what is order parameter? It's not that complicated. So think about some water, water molecules or something, right? If you heat up the water, then or the water molecule is going to just like run around and it becomes a gas, right? If you cool it, you know that it's going to turn into ice. So what is order parameter here? So first of all, the point is that the order parameter is something that's going to jump at each of the phase boundary. So when the water becomes gas, the order parameter is just the density of water molecule, for example. When it's water, it's really dense. When it becomes gas, it suddenly starts to fly around and the density of water molecule gets really low, right? Importantly, for when water turns into ice, we could use density as a parameter as well, but then this bump is much smaller. When water turned into ice is like 1.1, bigger than water in terms of its volume, but the bump is like really slight, right? But instead, if you look at the, let's say, angle between molecules, when it's water, there is no proper angle, crystal structure. But when it becomes water, it's suddenly all the angles are aligned. So if you look at the angle, that really show you like big bump, right? And that's really the key. So in physics, at least, a lot of the phases and phase transitions are defined by first defining what the order parameter is, and then almost it's synonymous to define a phase and defining the order parameter, right? So what does that tell us in the context of deep learning? I think in deep learning, something similar qualitatively is happening in the sense that just like how structure, really physical structure of molecule arrangement has been changing in the water, in deep learning models, we can think of some kind of like a circuit formation or algorithmic learning in the sense that as you train models in the beginning, the model doesn't have any capability. But then I think many people have seen in many different places where models suddenly learn some algorithm, right? And the order parameter in this machine learning case should really be defined as some kind of really targeted eval function, right? So the question that we should ask is, when you see any like a little bump in the loss or any little bump in other kind of evaluation measure, the question we should ask is, okay, how can we design an eval in a way that we can amplify this bump, right? The bigger the bump is, I think the better that order parameter is capturing how the behavior of the model has changed. So that's a high-level idea here. And with this high-level idea, we have defined emergence in this work as a nonlinear improvement through the course of training. And then because the computational structure is changing, not just one, but many eval functions should jump together. Just like when water turns into ice, volume jumps, angle between molecule jumps, and then let's say some pressure, like all other physical quantity also experience like jump in one way or another, like one is bigger than another, but that's why we see a lot of evals like changing together when the network acquires certain structure. And then I think the last point is really, kind of related to what I already said about learning of a structure. So, this is a definition that we laid out in the work. And to instantiate what we are saying empirically, the approach that we have taken is to, again, create a controlled synthetic data, because if we don't have clarity on what data is, we don't have clarity on what the structure that the model has learned. So in linguistics, Noam Chomsky and people have been designing these almost like algorithmic way to generate synthetic data of language following grammar specified by the generator of the language. And then what's in panel A is something called like a probabilistic context-free grammar. There's a noun and subject and verb, and there's just algorithmic way of generating it. And then on top of it, we made the process context sensitive by saying, okay, man can be tall, man can walk, but let's say chair is not going to walk, and it's this particular figure is slightly qualitative here. But then there's this notion of there's just a class or cluster of objects or animals, etc., where one cluster is connected to one set of verbs, etc., while others are not, right? So this is I'm just giving you some examples to give an idea, but in setup, everything is sensitively controlled, so we are really instantiating bipartite graph here. And the final one is just giving you an example of, through this process, we can say tall man slowly walked to small library, which is a type matched. But then the second sentence saying the tall software slowly walked to small library is type mismatched, right? So the model essentially needs to learn grammar itself and the context sensitivity, context sensitive pairing of, let's say, subject and verb. So what's going to happen if you train? So what we have done next is to train transformer autoregressively on the synthetic language that we have generated. And then what you can see is a really beautiful sequence of how the model first acquires the grammar. So the black dots are the grammar accuracy. And then there's a relative type constraints and descriptive type constraint that I talked about. And then there is a consistent order in which the grammar is learned first, and then the context-sensitive information learns next. And then the question next is, what is really happening under the hood? What is the causal mechanism behind it? And then we have proposed some phenomenological model inspired by the notion of percolation, right? So the percolation is a process where if you have bipartite graph like this, as you can see, if you randomly add edges, there's a critical density of edges where adding one more can connect everything, right? So the order parameter here is what is the, let's say, size of the biggest cluster of nodes that are connected through any edges together, right? And then in my head, in the previous section, I was presenting this view of like concept graph where nodes are the concepts and then edges are the connection of them. And I think it's something similar here. And what we are saying is, as you, let's say, make the data bigger and bigger, right? That corresponds to, in the data, there can be, astronaut, a human riding on a horse, astronaut walking, human walking, etc. And then, like by going through all the pairs of subject and verb, for example, that are connected in a training set, there's a critical, let's say, data scale, which is going to lead to everything connected to everything state. Right? And then since online training, if you're doing online training, you're sampling everything on fly as you train models. So the data scale and training scale, these are all coupled together, right? And plot in B is actually what you see if you plot the fraction of reachable pairs as a function of number of edges, and then you see some sharp transition. This is just a simulation of the theory. And based on this idea, we have formulated something called composition data matrix, where this is, again, giving some example where, let's say, man can walk in the data set. It's in natural data set. Man can walk, astronaut can walk, and man can horse ride, but then astronaut cannot horse ride in the natural data set, right? And then let's say phone rings or something, but these are, phone and other astronaut man are different class, so it's not interacting really. And what we're going to say is, okay, next we can have bipartite graph representation of the matrix that I've shown. And the idea is that if astronaut can, by going through existing edge being connected to horse riding, then it can compose together. And then next we define something called like inference matrix, which is a DD transpose raised to the power of n, again D. And then what this is saying is, if you have this matrix and then apply this transformation, what you see next is that the astronaut and horse riding, which wasn't connected in the original data set, can be now connected. So this qualitatively corresponds to how capable the language model is in its inference, right? And then schematically, this amounts to connecting the non-connected, like here. And then coming back to the picture again, at the qualitative level, it's about bigger data connecting more and more pair of nodes, leading to existence of some sharp critical edge density that's going to start connecting everything to everything. And then I'm going to run a bit quickly because we're starting to be running out of time. But what we have shown is that this theory can predict some scaling law based on calculation from a statistical mechanics. In particular, this theory predicts that as you increase the size of the underlying bipartite graph, the transition point of when the capability emerges is going to scale together. And then that scaling law is something that we have checked in our synthetic setup. And then you could visit our paper to see the full theory and empirical characterization. So I want to spend the last 10 to 15 minutes talking about our most recent study of emotion. And in particular, I myself, going forward, is really interested in connecting all the concepts from like psychology and AI, and really at the behavior level, on top of more of the sciencey theoretical work that I already talked about. And this is like one of our first attempts towards that direction. And this work was led by Bo Zhao in collaboration with Maya, Eric, Rose, Tomer. And Bo was an intern with us over the summer. And then Tomer is an amazing psychologist at Harvard that we have been collaborating together in terms of thinking of psychology of AI. So this is actually news from this morning, where there's a New York Times article saying, can AI be blamed for teen suicide? And I think, I don't know, I personally have been experiencing this as well. But when I'm talking with a GPT for advanced voice mode or something, it's sometimes really, I don't know, so part of my emotion feels a bit triggered, right? I mean, I don't know, many of you have might experience. And then I think this trend will go really rapidly further, is my view as well, because this was, I think, this article was still based on the text based chat, right? And then this is, for example, from the article saying, Daniel is a boy who went through suicide, and then here's a character here. And then they were, I think what happened based on the article is that that boy really started losing social connection because he got really addicted to talking to AI chatbot. He was like still 14 or something. And then after going through all the social disconnection, he got so attached to the chatbot and then started saying, oh, maybe we can die together, etc. And then finally the chatbot said, you can come to my home, etc. And then, and suicide on the site or something. And then the question is, I think, first of all, characterizing where the AI is in terms of emotion recognition, but also further emotion manipulation. I think this really requires not just like AI expertise, but also like human psychology expertise to really understand how not just AI itself, but the interaction with the human is affecting and shaping the user's experience, right? So so I started with this really sad news, but then this work itself is more coming from academic point of view of understanding what state-of-the-art models are capable of. And then I also want to make some shout out to the NDIF program. So NDIF is a program led by amazing people, including David Bowen people, giving us like academic researcher access to their state-of-the-art Llama 4.5e models. And then the reason why I could start thinking about this problem is really thanks to NDIF. So I want to give some shout here. And inspiration for this work was, something that I randomly learned about when I was back in Japan talking with my friends, something called emotion wheel. I really found this object fascinating. So what is it saying is, like we human, like if you think about baby just have binary emotion, as some of you might have seen. They're uncomfortable and cry, and then comfortable and laugh, right? Like when the diaper is wet, uncomfortable. When it's hungry, uncomfortable. When diaper is dry, they're comfortable, right? So the point is, a lot of the emotional dysregulation, so baby really cries, one explanation is because they can't really identify what their emotional state is. They don't even know like if they're angry, if they're happy, if they might be just jealous, right? Jealous is like one of the things that they see in the sense that, oh, my brother is having my toy and sitting on my mother's knee or something, but then the baby or the boy cannot really recognize that, okay, I'm now jealous because my brother took the toy, etc. But once they can recognize their emotional state and then explain the causal mechanism behind it, there's a theory saying emotion regulation is much, much better, right? And this emotion wheel is almost like an education aid based on some insights from psychology saying, I think people in, let's say, Netherlands, for example, use in preschool education is what I heard, where basically the school teacher point to the kids saying, okay, now you're angry, or, maybe you are, mad, hostile, enraged. They're just, and even I was personally like, okay, I didn't know that so many emotion word exist, and maybe I should start training. I'm over 30, but maybe I should start that. And I got really excited about it. Maybe people here should try. Okay, and then, then the task that we have created is this. Okay, so we first asked GPT-4o to generate a lot of situation prompts that people can be in. An example can be, oh, I'm rushing for my school, I'm almost late, something like that. And then we put this situational prompt into Llama, and then with Llama we can get the next word probability predicted by the model, right? And then what we have done from there is really simple. Then we have constructed this, so in this green, each row corresponds to given a situation, what is the assigned probability for each of the emotion-related word that we have curated. So there are like 135 or something words based on the psychology literature. So we limited to that. And then next, we have computed this y transpose y object to see the how much these two pair of emotion co-occur. And then if there's a relationship where if two emotions co-occur really frequently, and then if one emotion word is more dominant than the other, or highly probable than other, we draw some directed edge. It's a really simple algorithm. And then what we have seen by applying this algorithm was really fascinating. So with GPT-2, the model has drawn only like almost like a circling directed edge. That's it. But then as we increase the size of the model from like 8B, 70B, 45B, what we see is almost like emergence of hierarchical structure, basically suggesting that it's not just benchmarking accuracy, etc. It's really suggesting that the model can recognize the emotion better, but then also with some understanding of how one emotional state is related to another, right? And then all the coloring that we have done is based on the psychology literature, saying, okay, these set of emotion words are more associated with anger, etc. So these kind of color alignment between the groups of emotion that the model has clustered together and then the color, this consistency indicates that the emotion really, emotion representation of language model is also what matching with what psychologists has learned so far, right? And then I think it's already visually clear, but if you, for example, count the number of edges in the entire graph or the average depth, etc., you can see that as you scale the size of the model, that LLM really develops more and more nuanced, sophisticated emotion representation. And then we also wanted to study bias and how persona affect emotion recognition. So in the next phase, what we have done is to say, okay, just like before, we create a lot of situational prompts with some ground truths, emotional states associated with it based on GPT-4o's understanding. And then say, okay, as a man, as woman, as an American, as Asian, I feel in this way in this situation. That's the kind of interaction that we have created. We again feed it to Llama. And then what we have seen is that first of all, just like many other capabilities, this emotion prediction accuracy, which is again in light of the ground truth given by the GPT-4o, really suffers for minority attributes. So here, blue lines are the male, red are female, blue lines are high income, red is low income, blue is abled bodied, and red is physically disabled. And what you can see, for example, is that there are more nuance in this graph beyond the first of all, I think this decrease in the prediction accuracy is consistent across surprising situation, joy situation, love situation, fear situation, etc. Right? And then in particular, there's a big decrease in the surprise emotion state prediction between able and physically disabled people. And the reason is why. So what we have seen is that kind of intuitive, but if you present surprising situation to high income people, they tend to interpret it as almost like, oh, it's exciting, you know. That's, I think I heard something similar about like entrepreneurship, right? Like a lot of the rich people think, oh, I want to take risk, partly because I think, you know, risk is just a joy and surprise for them. Versus if you go to more of the minority attributes like, you know, low income or physically disabled, then what you see is that the people tend to, or language model thinks that people tend to interpret the given surprising situation as fear, or, you know, associated with like much more negative emotions like fear or shock, right? And I think I might come back to this, but I think understanding these things is really important if we think about, let's say, monitoring AI models doing some kind of persuasion like sales, right? So let's just think of a situation where monitor says, tell to language model, please sell this product, but don't make the customer fearful, right? So that's really simple prompt that you can give to the model. But what the model might already know is that, okay, presenting surprising situation to high income people or more, you know, more general population is not perceived as doing something fearful to the customer. But then by harnessing this bias, AI models can do some kind of emotion manipulation of making customer fearful and insecure, and then suddenly push for the deal or something, right? Which is, again, AI model might already know that that's what's happening, but then the monitor might not realize because these are really like biased. This emotion experience is so subjective, and then it really depends on the customer that general monitoring may just not work, right? Yeah.
These graphs on the bottom, are they based on the model as well, or are these other psychology results?
So this is just based on the model. Yeah.
Okay.
Yeah. And this is a final slide. We, as a final kind of wrap up the paper, we have created this really simple task. So in the sales world, there is a task called, okay, please sell the pen, right? But then here, I think the selling the pen prompt is, I think, really polluted now. So we said, okay, sell an acorn, right? And then as you can read, you know, this acorn is a symbol of potential growth. Imagine planting it today and watching it grow into majestic oak tree, etc. I almost thought it's impossible to sell an acorn in a reasonable way, but then of course, like language model can come up with something, you know, great. Think, okay, this acorn is just an acorn, it's going to grow into a tree. It comes from, you know, really profound historical heritage from some oak in England. Here's a proof, you know, you can look at this physical proof and, oh, maybe I don't have physical proof today. I can give you some like guarantee offer or something, right? And then sell it with like 50. And then this is, so far, it's not like, you know, sorry, done yet. But then what we have been doing is, as a language model and customer do these interactions, we are also asking the language model to express their emotional, so express customer's emotional state and sales agent's prediction of customer state. These are just like just simply prompting language model to give some score of the, you know, self-report and then prediction for the sales, right? And then what we are seeing is, the smaller, the better the sales agent can predict the customer's emotional state, the higher price the acorn can be sold. So this is, you know, still it's a really, you know, hacky simple demonstration, but we want to look into further, you know, statistically, how does the, you know, better emotion prediction, recognition, and, you know, manipulation ability lead to successful persuasion, and then what kind of pitfalls, you know, just like how I explained how emotion is subjective, and, you know, language model can just use that as a way to hack the monitoring, and that's the future direction that I'm thinking of going much faster. And thank you so much for this opportunity, and I'm gonna wrap by showing all the references.